Greetings, Algebra 2 students. I appreciate you finding time to get your notes taken care of. Today we're going to begin looking into a lot of the word problems that are associated with the exponential functions that we've been talking about. It's actually one of the more useful types of functions that we run across this year. A lot of applications, a lot of real world, everyday type problems that can be solved with these functions. Okay, today we're going to take a look at what we call, well, it's the beginning of a bigger discussion on growth and decay problems, which means problems that are both are either expanding or contracting in one way or another. And there's different types of growth and decay. Today we're going to look at what I call incremental growth and decay. So please copy the title as well as the objective. And our objective for today is to apply exponential equations in order to solve problems of incremental growth and decay. As always, anytime you need more time to copy down your notes, press pause and then hit play whenever you're ready to move on. One of the biggest complaints that I hear of students throughout my career in mathematics is the when am I ever going to have to use this question, which I kind of find to be a little bit of a silly question because let's face it, you have to learn the basics of anything before you'll ever be able to find or discover the applications of any of it. But here I believe you're going to be able to see pretty much a very quick, very direct application for how these equations can apply in our day-to-day lives. Okay, now the application of exponential functions allows us to define some common everyday situations, like I've already said. Now again, this is kind of the first entry into what's going to become a multiple day discussion of growth and decay. Okay, but some of the things, some of the topics that we're going to be having a look at are going to deal with topics like population expansion, discovering how the size of population can expand or grow over a period of time. Interest accumulation, which is stuff like, you know, when you invest your money in the bank or whatever, and they pay you interest back, or possibly when you borrow money from somebody, how interest accumulates against you. Chemical half-life, which of course is something that is important in dating fossil records and things like that, and radioactivity and how materials decompose over time. Computer processing power. This is something that's probably of interest to a lot of you. Is how they calculate the number of calculations per second, and things like 3G versus 4G. How do they decide when they've reached the next generation of data transfer? Foliage growth is also decay or exponential decay and growth, because like a blade of grass or a plant, it does not grow at a consistent rate. It grows fairly quickly right off the bat, and then slows down over time, stuff like that. And depreciation, which is the opposite of interest. Depreciation is how much your possessions, how much value they lose over time. Now, what we're looking at today, as I said, is incremental, which means a change that is occurring every so often. Okay, so we're watching out for terms like daily and weekly and monthly and yearly and things like every decade, every century, stuff like that. Okay, and when you identify problems like that, and again, this goes back to a previous discussion, the problems are not going to come out and say, hey, I am incremental, use this formula. Okay, you're going to have to identify what's going on in the problem and then come to the conclusion yourself that this is the formula that needs to be used because the problem is doing something incrementally every so often. And the formula is, as you see there, y equals a times b to the x. Okay, now this goes back a little bit. I talked to you earlier in this unit about the strange notation, having two different constants in the base multiplying together. And I said that it was a little bit of a strange notation, and many of you may wonder why I was doing that. Well, here was part of the reason, because there's actually two different pieces of information in the growth and decay formulas that are both working in the base together. Okay, now please remember your order of operations. Here, please excuse my dear Aunt Sally. Okay, that means that exponents must be dealt with before multiplication. And what that means is that the exponent x belongs to b, not to a. And it does not belong to a times b. It belongs only to b. That's going to be important. If you mess that up, you're going to mess up a whole lot of problems here pretty soon. Anyway, let's take a look at these variables. Okay, in this particular instance for incremental decay and growth, A represents the initial amount of whatever is going on in the problem. If you're talking about a population that is growing, or an amount of material that is decaying, or an amount of money that is being invested or gambled, or things like this, that is an initial amount. B in the base represents the rate of growth. Now, obviously, growth is kind of a relative term, because we can actually be growing, meaning expanded, or possibly a lack of growth or a removal of growth, which means we're ending up with something smaller. Okay, so there's going to be some things that can happen with B. One of the things that can happen is we're going to be on the number line. The magic number of 1 is going to be the dividing point, just like it has been all along. Okay, and B is most likely going to be on one side of 1 on the number line or the other. And if B happens to be between 0 and 1 on the number line, then this is a decay problem. If B happens to be exactly 1, then the problem is stable. It is not moving or growing or anything. In fact, the graph is not moving at all. We said back in the a few days back that we would discuss what happens if the base number is actually 1. Well, if the base number is actually 1, you just came up with a horizontal line. It is going to be a perfectly flat line, not increasing in either direction. So it actually is not exponential at all. And then the other side of it is that B can be greater than, that should say 1. So please make that a 1 right there. B can be greater than 1. And when that happens, the problem is growing. And if you think about the shape of the graphs, this should make perfect sense to you, because when your base number was smaller than 1, as you read the graph from left to right, what did the graph look like? It started up high at positive infinity, and then as you move from left to right through the graph gets lower and lower and lower. Okay, if your base value was larger than 1, then what did that graph look like? It came in sideways horizontally from negative infinity on the x-axis, but as you continued across the x-axis, the graph grew taller and taller and taller. Okay, so that should make sense. The graph, as you read from left to right, a B between 0 and 1, the graph should be getting smaller. That is decay. But as if B is larger than 1, as you read from left to right, the graph gets bigger. That is growth. Now, the variables that are left in there, X represents time. We have said that all along. If time is an issue in a problem, okay, it always is the independent variable. Time always gets the x-axis. Okay, so X represents the amount of time that has elapsed, and the entire function Y will equal however much amount there is at however much time has elapsed. Okay, it's a pretty cut and dried formula. It's actually not a real difficult one to utilize. All we have to do is plug values into it correctly, and we should be pretty much good to go. Straight in the calculator, straight out of the calculator, as long as we know how to ask the calculator the right questions. And that's something that some of you are still fumbling around with. We're still typing up a bunch of garbage in our calculator and then writing down whatever it says. Well, whatever it says has not been real good in some cases, and some of you are still just writing it down. Got to learn to ask the right questions if you expect to get the right answers. So let's have a look. Okay, let's look at a problem on population expansion. Now, this type of problem that we're getting ready to look at, it's not to say that it only works for population expansion, but it works for, obviously, population expansion as well as similar type problems. Okay, so let's take a look here. This is a common study that goes on, and this deals with rodent reproduction. So let's say two rodents reproduce at a rate of 1.6 per month. What would the population be after 9 months? Okay, first thing to identify is that this is an incremental problem. Okay, and we identify that by looking for phrases like per month. Okay, so per month suggests that something is happening and being applied after each and every month. So we're going to use the incremental formula, y equals a times b to the x. Okay, so let's have a look. A represents the initial population of the problem. Okay, so what is the initial population? What numbers do we start off with? We're starting off with 2 rodents, so that is our A value. A will be a 2. Okay. B represents the rate of decay or growth. Okay, now this time we are looking at growth, so we should expect a number larger than 1. Okay, and as it turns out, the problem does hand us this value, 1.6. Okay, so our base will be 1.6. And x represents the amount of time. Now, one thing that you do need to make sure of is you need to make sure that the language of your problem all agrees. Okay, so you notice the base number was 1.6 per month. So when we enter an amount of time, we need to make sure that our time is entered also in months. We wouldn't want one value to talk in terms of months and then a different value to talk in terms of years. So we want them both to talk in months, and they both are talking in months. So we have an agreement in the time. All we have to do is plug our numbers in. Okay, 2 rodents, that's our A. 1.6 is the reproduction rate, that's B. And 9 is the number of months that elapse. So all we need to do is get it into our calculator, make sure that we obey the order of operations. 1.6 to the 9th needs to be dealt with before that is multiplied by 2. And over 9 months, your 2 rodents became 137 rodents or mice or whatever you want to call it. So I hope you like the little furry friends because you just ended up with a lot of them. Okay, let's look at another one. Compound interest. This is a typical banking type formula. Okay, if you invest money, you would like your money to be compounded rather than simple interest formula. I think everybody knows that old simple interest formula of interest equals, or I equals PRT, principal times rate times time. You've worked with that one over the years. That is a bad formula. You do not want your investments operating on the simple interest formula. You want it operating on compound interest because that means that your money earns interest, and then that interest also becomes your money, so it also earns interest, and that becomes your money, and then that interest also earns interest. The simple interest formula does not do that. Compound interest does. Okay, so let's take a look here. A couple invests $10,000 in an account that awards 2% interest each month. After 4 years, how much will they have? Now, 2%, that does not sound like a very good investment, but the fact that it is compounded monthly, that is a good thing. Okay, 2% per year would be bad. 2% per month, that's pretty good. Okay, so let's take a look here. We need to make sure we're going to use the right formula. Okay, how do we know if we're using the incremental growth and decay formula? We want something to happen every so often. And we see in this problem the wording each month. Okay, so that is happening on a repetitive time basis. That means we're going to use the y equals ab to the x formula. Okay. A represents the initial amount of whatever is happening. And in this case, that would be a $10,000 investment. They're going to put $10,000 in the bank. B is going to be how the growth or decay is actually happening. Now they are earning interest on an investment of money. So that is a growth. So we expect our value to be larger than 1. Okay, well, the value that we have here is 2%. 2%. Now remember, percentages do not go into problems. Decimal points go into problems. Okay, so what is 2% as a decimal point? It is 0.02. Now, is 0.02 larger than 1 on the number line? Well, of course it's not. It's down near 0 on the number line. Okay, but remember, this is money earned. Okay, are they going to lose their original money? Of course not. They're earning more money on it. So they still get their original money. So that is 1. That is 100% of their investment. They still have their $10,000, but they're going to get more than that $10,000. So instead of being at 1, which would represent just having their $10,000, we're now going to go 2% higher than that, which would be 1.02 each month. Now, the problem also talks about 4 years. Now, pay attention to your time. The interest is accumulating each month, but then they ask us how many, after 4 years. Okay, so what we probably want to do is we probably want these 4 years to instead of talking to us in terms of years, probably be better for them to talk to us in terms of months, just like the interest is talking to us in terms of months. So what I've done is I have turned the 4 years into 48 months. Of course, I've done that by saying that there's 12 months in a year. 12 times 4 years is 48 months. So $10,000 is the initial investment. 1.02 is the interest or the growth rate. Again, the 1 because they do get to keep their original money or they're going to get it back. And then the 0.02 to show that it is increased by 2% and then raised to the 48th power. Now again, all we have to do is figure out what's going on with this number. Pay attention to your order of operations. 1.02 needs to be raised to the 48th power before that is multiplied by the $10,000. The result of that, cha-ching, $25,000, $870.70, 28,870.70. That is an amazing investment. Okay, they almost tripled, or I'm sorry, or they multiplied their money by time and a half in just 4 years. If you can find an investment like that, you need to jump all over it. Okay, let's look at one more. Depreciation. Okay, this is something that's going to cause a bunch of people a bunch of heartache here, especially here in the Permian Basin. Once our oil explosion, our oil boom levels off, which it will. I've lived in the Permian Basin, or at least West Texas area, since 1996. This is the third oil boom that I can remember. Everybody always thinks it's going to last forever and they're going to have all this great money forever, and there's no reason for them to invest or save or not splurge on items, and every time it fades away and all those people end up basically being broke because they didn't manage their money well. So here's a perfect example. You see this driving around the streets all the time. You buy a brand new Super Duty diesel dually pickup truck for $82,000. All these people driving around these gigantic trucks that they don't need, actually driving them like they think they're race cars, dumping exhaust all over the place, all that good stuff. At any rate, the annual rate of depreciation for an automobile runs about 15%. Okay, and that's pretty much a standard across the automobile industry. So let's say you take your $82,000 truck that you did not need, but you bought it because you had more money than brains. And then after 4.5 years, You lose your job, the oil boom recedes, and you decide, wow, I can't afford to have this truck anymore. I need to sell it off and get my money back. And we're going to see how much you can probably expect to get for your $82,000 truck that's not even 5 years old yet. Okay. Now we need to look and see what kind of formula we're going to use. Again, this is exponential growth and decay. So we are going to use our formula, okay, for this because as it says, it's an annual depreciation. Y equals A times B to the X. Okay. A is your initial amount. That's the $82,000 you dropped on the truck that you didn't need. Your base is your depreciation. Now it says it depreciates 15%, but as we already said, 1 on the number line, that represents your full money. Okay, that is 100% of your money. So if it depreciates 15%, well, we're not going all the way down to 15%. We're saying we have lost 15% of the original money. So on the number line, that would come from 1 back down 0.15. So that would actually put us at 0.85 on the number line. The amount of time that has gone by is 4.5 years. Okay, the depreciation was in terms of years, and the problem is also in terms of years. So we ought to be able to just plug those numbers straight in. Again, $82,000 is the initial investment. 85%, that 0.85 sitting there, is how much of your value is still left after 1 year. We lost 0.15, so it came down from 1 to 0.85. And 4.5 is the number of years that you have owned this truck that you didn't really need in the first place. Okay, so after 4.5 years, how much money should you expect back for your extravagant truck? You should expect to get under $40,000. You've lost over half of your investment in less than 5 years worth of time. A lot of people in this area are going to be feeling that kind of a pinch once this oil thing recedes a little bit, where they've made all these investments and they weren't smart investments, and they're going to end up losing a whole lot more money than they realize when they lose that job. At any rate, this is how the exponential growth and decay formula works. I do appreciate you finding time to get your notes taken care of, and I will see you in class.